Exercise 106. Let's talk about the multiplicative group of FracR. In other words, CP flat. Multiplicative group. So, first exercise, prove that there is canonical isomorphism of Z modules as follows. So, we take the fraction field of R, take its unit, its multiplicative group, and we claim this is isomorphic to the Z module of homomorphism of Z modules from Z1 over P. So CP, so let me be consistent, we called it CK before, CK multiplicative group. Okay, so idea is that so as Z module map, right? So F here not necessarily equals 1. It's just the Z module map, right? While actually F1 equals 1 actually implies that Fn equals, so here this is actually the additive abelian group, there is a multiplicative one, so Fn is F1 plus 1, n times actually gives you F1 to the power n gives 1, which means F1 equals 1 actually is telling you that for any integer and this is 1. One more thing, so what is the relation of F1 over P with F1? So F1 is actually this. Again, this is 1 over P to the power P. So you see the relation. The image of 1 over P is P root of F1. Okay, let's start the proof. Let's consider the following map. Construct a map with alpha from this Z module to fraction field of our multiplicative group. So let's map this any element F to P to the power minus n and the nth component. So let's check this is well defined, which means on the right hand side this is indeed here, and then we show this is bijective, right? So just quickly notice that F P to the power minus n is just F P times P to the power minus n plus 1, and so this is F P to the power minus n plus 1 to the power P. This is okay. Now let's check alpha is injective and surjective. It's injective is because F p to the power minus n equals 1 for any n, imply that f1 equals 1. This, as we remarked, equal implies all the integer has its image equals 1, and also for the p to the power minus n equals 1 together is telling you that f equals 1 over, right? This is the nerd element target. Surjectivity. So for any element on the right hand side, let's construct a pre-image. So we define f as follows. Say key star by map f0 to 1, and then f1 is defined to be x naught yeah, f over p to be f(x1), f over p squared to be x2, etc. Right, then this works. Second exercise, so let's prove some isomorphism results. 2.1. Multiplicative group of R is isomorphic to this is what we just proved. Let's prove also the unit group. It's defined to be group of units of R. It's isomorphic to similarly 1 over p to OCK star. We claim this is isomorphic to the residual field, multiplicative group, product with UR plus, where UR plus is defined to be elements of R such that its component is in U C K plus. What is UCK plus? UCK plus is defined to be 1 plus maximum ID of CK. 2.3 U R plus defined here, claimed to be isomorphic to say linear map to U C K plus. So you see this, anything happened here in R, it's could be written as Z linear map from Z1 over P to corresponding things happened in say K. FracR corresponds to CK star. O FracR star corresponds to OCK star. Unitary group. In other words, unit 1, right? This is sometimes write as a unit 1. I think it's better to write unit 1 group. This is the more standard notation. R is corresponds to unit 1 group of CK. This is again claimed to be isomorphic to yeah, this is not actually UR1. UR1 is usually it's because we were talking about discrete valuation ring. In that case, UR1 is UR plus, but here is not necessarily discrete valuation ring, so plus really telling that it has positive valuation for x minus 1 have positive valuation, right? Because really we have a UR1. What should be UR1? UR1 by definition should be defined to be those have exactly valuation bigger or equal than 1. While UR plus, you could imagine, should be defined to be those valuation x minus 1 bigger or equal than 0. Lastly, UR1 should be isomorphic too. Firstly, let me recall the definition. Yeah, x in R. Let me write here just. Isomorphic to inverse image quotient by p power ideals or p power subgroups. Let's prove some of it. So let's say 2.1 is already proved. So let's just notice that by exactly the similar arguments, we should be able to prove that OCK star have map to R star. R star is here denoted as UR. by map f to, again, f p to the power, f p to the power minus. Firstly, so this is telling that f1 is in OCK star, f p minus 1 is in OCK star, and the pth power of this equals f1, and this equals pth power fp minus 2, still in OCK star, etc. And so obviously this is compatible with Frobenius transition maps. And so here on the right hand side, each component lies in OK bar hat, so OCK. And some over the sorry. So what we have to show is that this is contained in here, right? This is true because as we recalled, what is this? Our star is those such that x0 is a unit of OCK star. Actually, when x0 is OCK star, and then because x1 would be pth root of that, and then further x2 would be a p square roots of that, and all this would be units. Anyway, this would be obvious. And so this is well defined. And then similarly, one could show that this is surjective and injective. Or you could just argue by already proved lemma, or exercise 1, that you already proved the isomorphism between FracR star and homomorphism from ZE 1 over p to ck star, and then we are selecting all those elements of FracR star such that the first component is not only in ck star but also in ock star. And when you're doing this, this corresponds to exactly those z-linear maps from z1 over p to ock star. Because firstly, you must map f1 to something in ock star. Secondly, once you map to f2, f1 to ock star, then automatically f1 over p will stay in ock star, because it will have again positive addition. Non-negative addition, right? And again unit. So again in ock and also in ock star. And so that's it. Secondly, let's consider the map from O, C, K star surjective to K bar, map element X to X mod 1 plus M C K. Not just mod M C K. So those are the elements such that X does not congruent to 0 mod MCK, right? Which means X not in MCK. And the residue field is isomorphic to OCK quotient by MCK. And so the kernel is exactly the preimage of 1, which is then 1 plus MCK. This is what we call UCK plus. Well, that's not enough. This actually splits. There exists a section from K bar star to OCK star. Wow, you could think of this tachymeter lift. So think of it this way. So through Teshmeter lift, map into WK bar. This is actually corresponds to this is injective map, because this is map element X to this, and this embeds also into 1 over P invert. This is K ramified completion, and this is contained in C key. Okay. And so remove invert P, this is contained in OCK. And so it splits. OCK is isomorphic to residue field product or direct sum as Z module. So in other words, residue field, and then look at your valuation. So those contribute nothing to valuation, those contribute to valuation. Okay, not accurately. I mean, so here's star. When you but you are, doesn't matter. So you are. So when you modulo maximal ideal is not 0, then your structure could be determined by an element of K bar star and element in the group UCK plus. As you could imagine, elements in 1 plus MCK, those are unit elements. Those are all, not all, but those are units of OCK, because modulo maximal ideal, this is 1, and so non-zero. Wow. What are the other possibilities? The other possibility that modulo MCK not necessarily 1, but any non-zero element in the residue field. K bar stars. Okay. And then by our first, by our second checkrization of UR. So now we have new checkrization of OCK star. This implies UR could be also written as, this is what we have proved, just proved. Here we put OCK star, but this OCK star now it has a new structure or new description, and so we could write this further as homomorphism, linear maps. 1 over P K bar times linear maps 1 over P UCK plus. This is isomorphic to K bar, because actually the f is uniquely determined by f1, because f1 over p is some p root of f1, but because this is a perfect field, then there is a unique one, which means once you define f1, f1 over p is exactly the unique p root of f1. And what is this? What is this structure? This structure is claimed to be isomorphic to UR plus as we just described, those elements of R such that all its component in UCK plus. So now it's left to prove 1 over p UCK plus UCK plus is 1 plus MCK. So isomorphic to this UCK plus itself. Wait. UR plus. Yep. Yeah, we want to prove this. So again, by our first exercise today, so everything is still under on the same platform, which is here. We just put CK star that corresponds to multiplicative group of FracR, and say this UR plus what corresponds to those not only in CK star but also in M plus MCK. But notice that actually to have this element in UR plus is equivalent to all the FP minus NAZ UCK plus actually is equivalent to just F equivalent to F is mapped from F over P to 1 plus MCK, right? Because if all the FP to the power minus n there, then the image of this is obviously here. out. I think moreover, this is also equivalent to those elements such that x0 is there. Because if x0 is there, then x1 must be there. Just a small remark. Am I correct? For example, if x1 is 1 plus some m, then x0 is 1 plus some m to the power p. And characteristic p is 1 plus m to the power p. And if m is in the maximum ideal, then again this is a maximum ideal. Yeah, this direction is okay, but the other direction, yeah, you take p-th root, requires some work. Okay, anyway, this is okay. Lastly, let's consider UR1. Those elements such that it's very similar as local field case. So those elements valuation is bigger or equal than 1 minus 1. Particular this UR over p to the power n would be those elements. Bigger or equal than p to the power n. Now consider the following map. Going to construct a map from UR1 tensor over ZP with QP to UR plus. So I take any element of this form. I can always write it uniquely into this form, just move all those numerator to the right hand side through this ZP module structure. I just map it to u to the power p to the power minus. This obviously have, I mean, if we u minus 1 is bigger or equal than 1, then u to the power p to the power minus 1 is still positive. Because this is bigger or equal than 1 implied that valuation of u should be wait 0, and if 0 0, then this is, if the 0 1, then it will be 0. Yeah, if it's bigger or equal than 1, then this is implying that we're taking from the non-zero, so this must be zero. Wait. Anyway, let's just argue that p to the power minus n minus 1 to the power p power to the power n is u minus 1. And so this must have positive valuation. Okay. So for any element, actually, UR1, by definition, u minus 1 bigger or equal than 1, and then there is this sum such that p to the power n times this valuation is bigger than 1. Wait. I mean this. I want to show surjectivity. Then just this element is in QP tensor ZPU1, right? And this is mapped to x minus 1. Oh, what did I write? So this is in UR1, UR1, sorry. This is also way of x to the power p to the power n minus 1. This is implying this element x p to the power n is in UR1. And so this is mapped to x, right? So it's surjective. For injectivity, if that is 0, then if you reason to some p power 0, I mean, of course, 0 is mapped to 0. Because this is positive valuation, it cannot be 0. We're taking just p throughs because if that's 0, yeah. So it's injective because if this is 0, then u is 0. So this is injective. So prove this isomorphism. Last exercise. Let's consider the element. It's denoted by this very standard notation, epsilon, where epsilon 0, let's call this epsilon, or sometimes call it epsilon bar. Epsilon 0 is the unit, and we take a p through of it, but we don't require, it's a primitive p through that, in other words. And then we just require this is element of R. So it satisfies this transition map. In other words, this is primitive p-nth root of unity. And then the exercise asks you to prove this is a unit of R. solution. Actually, I think it suffices to just show that epsilon 0 or epsilon n. It suffices to show this is not in the maximal ideal of CK, right? Because as we know, yeah, this is exactly those such that x0 is in CK. With OCK unit, right? So this is to show this is not there. Oh. Yeah. Yeah, but this is 1. And so it's not there. I think this is quite obvious. Let me put the sub-exercise. Compute the valuation of epsilon minus 1. Okay, then by definition, so let's look at this. 1 minus 1 minus 1 would be, so let's say p is not 2, then this is epsilon minus 1 would be minus 1, because of minus 1 to the power p, which is odd, so again minus 1. And then epsilon, or yeah, the nth component of epsilon minus 1 by definition would be the limit m goes to infinity, epsilon m plus m minus 1 plus m, which is minus 27, raising to the power p to the power m. Let's call this pi. Then this is pi n just. Right, by construction or by definition, it's pi n. And so if you compute the valuation of pi n, this will be the valuation of limit of p to the power m times epsilon let me first compute pi 0. this will be just m minus 1. This would be so the extension p-adic evaluation of epsilon to the power m minus 1. This is what we know. Should be primitive p to the power m through to the unit evaluation of this. So this should be p to the power m minus 1 times p minus 1. 1 over that, and then times p to the power m. This is just p over p minus 1. So I put this as a sub-exercise. Same corresponds to the Euler number, right? Maybe that is totally ramified extension. And with this uniformizer, what I mean in my mind is that, for example, if I have Q, that's p to the power. So the characteristic of the residue field is p. In that case, this is totally ramified. What is the Galois group of this? Galois group of this should correspond to so primitive, so comes from the character. I guess this is just, maybe it's this, right? That would be totally ramified. The ramification index should be Euler number of p to the power m. This should be p to the power m minus p minus 1. I guess it comes from there. And so you could have also, what is this? This would be a pth root of pi 0, right? P to the power n, maybe this. If I'm correct. If I'm correct. Okay. And from here you could also say all those elements have positive valuations. This is even bigger than 1. Does it really matter? It's bigger than 1 or not? I don't think it really matters. This is bigger than 1 or not. And similarly, one could compute the case when p equals 2. P equals to actually a very similar argument. You will see that you actually computing the limit of 2 to the power m times in that case the only difference is that minus 1 would be 1. And then let me write it down. by the formula this is. So let's say, so like valuation of this is valuation 1, and the valuation of this is 1/2 to the power n minus 1. Sorry, this is similar argument as before. Similar arguments. I mean, it's bigger than 1. But this is smaller than that. And so by the Nash mean evaluation property, so this should be the minimum one, which is this one. This is 2, but 2 also fit into that formula of p over p minus 1. Anyway, both we will see this is good.